As a part of the faculty development program, effective ways to develop e-content for teaching learning, organized by the Regional College Nashik and Savitribai Pune University Pune, as a part of assignment for day 1. I am preparing this video on the topic superconductivity. The content of for this 10-minute lectures are: first of all, I will introduce the superconductivity. Then I will go for the properties of superconductors. Then we will discuss about the VCS theory, that is Bardic, Cooper and Slipper theory. Then there are certain references used for this. First is engineering physics by Ivan Sirsagar, Electron Contribution, and introduction to solid state physics by Keaton. So we will start with the discussion. First of all, what are the superconductors? Definition of superconductors. Superconductors means we say that there is 100% electrical conductivity, or we can say that zero resistivity. So when resistance of any material is zero, means having 100% electrical conductive nature of that material we will call it as a superconductors. So in superconductors, what happens to the electron, so that they will not possess any resistance when they will travel to the complex, that is, there is no obstruction. So because of they bump into nothing and create no friction in the lattice. Due to no friction, the material possesses the zero electrical resistance. They can transmit, electron can transmit the electricity without appreciable loss in current and without loss of energy. So first time, this is the Dutch physicist. The Dutch physicist is K. Once, called as common name Once, and he was doing the experiment for measuring the resistance of the mercury, that is Hg, with temperature. So how the variation of resistance of this mercury takes place with temperature. And he observed that when the temperature of this mercury is decreased and the resistance of this mercury abruptly becomes zero at certain low temperature, that is 4.15 Kelvin, and he surprised that what happened, so that the resistance of this mercury is becoming zero at a lower temperature. So when he was doing the experiment, what he was observing, he was decreasing the temperature, he was going towards the zero temperature from here to here, and he observed that the resistance goes on decreasing. But at particular temperature, like 4.15 Kelvin, he observed that the resistance drastically or abruptly becomes zero. This temperature is important, and he observed that if we take different material, he has taken initially mercury, but he will take different material, the temperature is different and this TC point is different for each material, here the resistance is abruptly becoming zero. So if you are having below this temperature TC, less than this temperature TC, or less than 4.2 Kelvin for mercury, the resistance is becoming zero. But if you go above the TC, the resistance is not zero, it is again behaving its normal state. So he awarded the Nobel Prize in 1930 for his investigation to study the properties of matter, various matter at low temperature. So for his study, he defined the superconductivity. So he has plotted the temperature on x-axis and resistance of a material on y-axis. He observed that when we are moving from high temperature to low temperature, the resistance is dropping to zero. But when we are going at certain minimum low temperature, at that time the resistance drastically becomes zero, and below this temperature, if you are again reducing the temperature, resistance of the material remains to be zero. There is no change in the resistance, but it remains zero below this temperature. So this temperature is point, that is TC, called critical temperature. So phenomenon of sudden disappearance of electrical resistance in a material below a certain temperature is called as superconductivity. So above temperature, critical temperature Tc, the material is in normal state, and below the temperature Tc, the material goes into its superconducting state. So superconductors are the materials that exhibit superconductivity and which are superconducting state are called as superconductor. Aluminium, tin, mercury, lead are the examples of superconductor. So for every material, this critical temperature, this point is very important. If you study the various metals or different metals, the critical temperature of aluminum is different, critical temperature of lead is different, critical temperature of mercury, which is 4.2, it is different. So temperature at which material moves from its normal state to the superconducting state, that temperature they are calling it as a critical temperature. Every superconductor has its own critical temperature at which it passes over the superconducting state. Okay. So the critical temperature of various metals are like this. For aluminum 1.1 Kelvin, for tin it is 3.72 Kelvin, for mercury already we have seen 4.2 Kelvin, lead it is 7.2 Kelvin. It goes on increasing. For different it is 90 Kelvin. If you go for 133 Kelvin, it is. So we are going higher critical temperature, and our aim or our motto is that the material should behave as a superconductor at room temperature. At room temperature means this critical temperature should be up to 300 Kelvin. That is the challenge in the field of superconductivity. So what are the different or various characteristics of these superconductors? First characteristic of superconductor is they show zero electrical resistance. Second characteristic is they shows the isotopic effect. Then they shows the Meissner effect, and they shows critical field. Last, they show the persistent currents. Basically, two things widely used to study the superconductivity. First, Meissner studied the superconductor, and he explained why this happens or what happens when material goes to the critical temperature, or why the material shows the zero electrical resistance at or below the critical temperature. He given a simple statement that he says that at superconductors or at superconducting state, the material completely expels any external magnetic field lines. Whatever external magnetic field lines are there, they are completely expelled by the material at its superconducting state. So what happens? You could say in the normal state, this is the material which is placed in the normal state, and you apply the external magnetic field. Normal state means T greater than critical temperature. So when you apply the magnetic field, what will happen? All the magnetic lines are passed through the material. This is a material, so this material also has its magnetic field, right? And this is another magnetic field which we are applying externally. So at normal state, all the lines passes through the material. But if you decrease this temperature less than Tc, what will happen? The magnetic lines which we are applying, that are expelled outside, that are coming outside. Means inside this material there is no magnetic field present. That's why it is expelling all the magnetic lines of force. He explained that superconducting state is a perfect dielectric field. Perfect dielectric field means what will happen? The magnetic field inside the material is zero, or it has negative magnetic susceptibility. How he has explained? He said that this is external magnetic field applied H, which we are applying. The magnetic induction inside the specimen. H is magnetization produced within the sample. Then at T greater than Tc, at normal state, what is the relation between these two? D, which is magnetic inside the basic magnetic field inside the specimen or inside the material, is sum of external magnetic field applied times the magnetization produced. If external magnetic field is 0, we can say that E is equal to 0 times M. But H is applied magnetic field. But when you go T less than Tc, that is in superconducting state, the magnetic field inside the material becomes 0. So D is 0. When D is 0, what we can say that mu 0 h plus n is 0, so h is equal to minus n. So the ratio of m upon h is minus 1, which indicates that there is existence of perfect dimagnetism. Direct dimagnetism exists for the material. So what Meissner said, that expulsion of magnetic field when material goes below the critical temperature and the material is perfect dimagnetic material. Another three scientists came together. One is Bardeen, another is Cooper, and another is Schrieffer. So named as Bardeen, Cooper and Schrieffer theory, given as a BCS theory, and they have explained what happens in the superconductor state. So key concept is electron-electron interaction via the phonon. There are electrons in the lattice of a material, and these electrons, they are interacting with each other with the help of phonon. Okay, so these phonons join two electrons from the pair called as a Cooper pair. So the electron approaches the ion. These electrons approaches the ions. What will happen in lattice? This free Coulombic interaction between the free Coulombic interaction is, this is lattice points, positive lattice points, and this is electron which is moving through the lattice. So what will happen? These lattice points are positive charge, electron is negative charge. So there is Coulomb force of attraction. So what will happen when electron moves through the lattice? These positive charges, both they will try, this positive charge will try to the electron, this positive charge will also try to move towards the electron due to the attractive force. So they will come towards each other. These positive charges, they will come towards the electrons, and what will happen? They exert the force on the electron so that electron moves very fast within the lattice. So automatically the second electron comes, increase in the density of ions in the region of distortion, slight increase in the positive charges, and they will exert a force, and increase in the positive charges attract another electron. They form the pair known as Cooper pairs. In this type dense clouds of electrons, such a Cooper pairs are formed. So this is the cloud, and this is Cooper pair that moves through. What will happen when Cooper pair comes? The lattice points exert a force on the Cooper pair, but when Cooper pair goes ahead, they will again go to their original position. So that's why the pairs move through the hole. So these are the interesting points. Key concept is electron-electron interaction via phonon. Electron approaches ion, that is lattice. There is a Coulomb attraction between electron and lattice ion. The interaction produces distortion in lattice known as phonon, and the increase in the density of ions in the region of distortion, slight increase in positive charges around electron E1, increase positive charge attract another electron E2, and this E1 E2 forms the Cooper pair with the help of phonon. The dense cloud of electron pair drift cooperatively through the material. The same velocity due to high density, even large current requires only a small velocity, hence minimizes the collision and hence diminishes the resistivity. Thank you very much.